Okay, so I did mention we could redo the numbers several times. Let me show you how to do that. Go to properties and then go to simulation main, or go to simulation main and then ask properties. And then you'll see there's a piece down here, randomness, and you can go ahead and change this. So let's just try this. There's a fixed seed. I'm going to make this some other number. And let me just check that that is what I'm getting, 1, 2, 3, 4, 5. And then let's just run it again. So I'm going to stop it at 75,000. Again, the 50,000 is the number of agents that it can generate. Maximum divided by 0.65 is more than 75,000, but I'm going to stop it there. And then we will just run it all the way to completion. So now, I'm close to the 8.8 and the 13.6. You could do, several runs and just average them out, if you want to push it that far. The next thing I want to look at is the MM3 model. So here we're doing pooling. So I'm going to just annotate this briefly and just explain what it is. So here are those original 3 arrival streams that we had coming at us at 39 per hour for each of the 3 barista lines. All right, now we're going to just collapse them all into one, and then they get served by this pool of, so there's a waiting line here again, and then there's these 3 baristas. They're each doing 43 per hour, right? And they're identical. So this is an MM3 model, and I'm going to show you what the analysis looks like. Just go in here. So I'm going to clean this up and just show you string theory 3. Now 39 times 3 is, just get our calculator going here. So it's 40 times 3 minus 3. So 127, right? Oh, sorry, it was 39 times 3. 117. Yeah, 120 minus 3. Okay, so 117. The view is the service rate of a server, the 3 of them. We'll go ahead and calculate results. And so what we're looking for now is 8, instead of 8.8 and 13.6, we've got 8 and 4.14. So the waiting time is going to drop significantly as a result of the pooling. That's the whole reason for going after pooling. So the question is, how can we modify our model to get there? First thing I'm going to do is I'm going to give us 3 baristas. There they are. And nothing else other than the arrival intensity needs to change. So remember we had 0.65 per minute. If I multiply 0.65 times 3, so that's 3 times 0.7, 2.1, minus 0.05 each time, minus 0.15. So that gives me 195. 1.95. Okay. Again, this is an MM3 situation where I have a Poisson process for the arrivals. In fact, one can formally prove that if I take 3 Poisson processes with intensity 39 per hour and I lump them together, then in fact I do get a Poisson process with intensity 117 per hour. Okay, I think that is all I need. So again, I want an expected queue length of about 8 and then 4 point something on the waiting line. So let's just verify that we're going to get that. Now I'm going to simulate this one for 25,000 minutes because it's 50,000 divided by 1.95, which is almost 2. So 50,000 divided by 2. So let's just go and fix that up. I could go a little higher, but I'm going to just make it 25,000. Let's run it for a little while so you can see what's going on here. The utilization, incidentally, of this system going from MM1 to MM3 remains the same. So we've got the same number of customers coming at it with the same amount of service. So it's running at 500 times now. Queue length is 6. I'm expecting about 8. Waiting time is 3. I'm expecting about 4. And now let's just go ahead and push this all the way to completion. So there's a 25,000. So I'm getting 3.76. I'm expecting 4 and 7.34. And again, you could do multiple runs here. The utilization is a little bit lower. Let's just rerun this one with, so I go to view properties and then I click on simulation main. Let's try that again. View properties. There it is. And I just make this, let's say 12 now. This is just some sort of initial seed for a random number generator. So the key point is just to have a different number there to get a different stream of results. And I want to view my projects. View the palette, excuse me. How do I get my model back? Man, there it is. Okay, and I'm going to simulate this guy again for you just so we can see how it played out. So I want to go to 25,000. Again, that's 50,000 divided by 1.95. Just being, conservative on there. And then I run this to completion. So now I'm getting 428 and 8.39. So that seems to be pretty close to what I saw off the queuing results. All right, so that's the MM3 model, and these are good estimates. Now, unfortunately, human service is unlikely to be exponential. It's usually some sort of maybe more normal, maybe it's sort of a truncated normal. So what we're going to need to do is to fix our service time distribution. So I'm going to go back to the single server setup where we have separate lines per server, and I'm going to change that. The Poisson arrivals remains the same. All I want to do is I want to change the number of baristas here back to 1. Okay, and then for the make coffee, here's a little bit of a idiosyncrasy. It's going to be normal, and then it's the standard deviation first, comma the mean. So I'm going to put in, let's say 0.25. I think that corresponds pretty closely to the situation where you have an 82% reduction in the variance that we had, or the standard deviation that we had for the initial setup. So in an exponential distribution, the mean and the standard deviation are identical. And so the standard deviation would have been 0.717. And if I take 18% of that, I think I'm getting about 0.25. We can check those numbers. Let's just have a look at that. 717 times 0.18. If I have an 82% reduction, I'll have 0.129. Well, yeah, maybe I messed that up. I'll just use 0.25. And then I'm going to use 0.717 as my mean. So I think we're doing, and I think I have to have another 0 in there. Just to make sure that I just try and run this. Yeah, don't need the 0 in there. Let's try that. Apparently I don't need the 0. Now this one I can run out to 75,000 again. So let's do that. Because it's only got the 1. Try a little while. Now I don't have a way of conveniently checking this. Maybe there is an MG1 calculator that you can find somewhere on the internet, but I don't have it in hand right now. So I'm going to rely on these simulation results. We're going to run it all the way out to 75,000 minutes. And, oh, yes, I see the problem. So when you set this delay up for the normal, when you do the exponential, you have to do rates. But when you do the normal distribution, you have to do times. So let's just figure that out. Let's get my calculator back here. So if it's so the number of minutes 60 divided by 43, it's 1.395. minutes. And the standard deviation, if I take 82% of that, maybe that's the 0.25 that I was thinking about, times 0.18. Yeah, there it is. Okay, so that's the 0.25. Okay, so important, when you're working with exponential, you're working with rates, but when you're working with a normal, you actually have to use the mean and the standard deviation of the inter-arrival time. Okay, so now let's run this and just see what we get. So let's set this up to get us to 75,000 again. Let's just see how it's going. It's clearly a problem. Let me just stop this. Just check what I have in here. So it'll be the mean, the standard deviation, the mean, and these are in minutes. Yeah. Okay, so let me check this. I'll just stop the video briefly and see what's going on. And then I'll bring you back. Okay, I quickly realized that, we've still got this arrival rate set up for lumping all three streams together. So when we're solving for the single server setting, it can only be 0.65 coming at us. So let's run that now and just see how it goes. Let's just crank this up for a little while just to make sure we're staying reasonable. That looks about right. And I'm going to simulate this out to 75,000. Okay, and then run it to completion. Now, there's a drastic reduction that's going on here in the variance because we're working with 18% of the variance, and it's also normally distributed. So the line length is much lower, 4.52 average, and then the waiting time average is 695. This is the mean weight here. This is the mean Q length. So L sub Q and W sub Q. And the utilization is 0.914, and you could rerun this a few other times. So that is the MG1 model for the setup. And I'll stop the video here and then bring you back for the MG3 model.